In this tutorial, we're going to create a custom shader. You can always add custom shaders with this viewer add custom shader function. You give it a name, a vertex shader, type D if you want the default vertex shader, and then a fragment shader. You always have to define the fragment shader. It'll tell the viewer how to render each pixel. The viewer demo comes with a few custom shaders. We have one which turns the image blue, as well as this takes the square of each pixel and the square root. So to make the shader, use the viewer add custom shader, and I have this blue fragment variable. And so where this blue fragment is stored is if you go to your server files and go to scripts, custom, scroll down to the bottom, you'll see I have this blue fragment as well as a bunch of code. So let's make this red instead. So copy and paste your blue fragment, name it red. And here in our BL function, instead of making the red and green half their value, let's make red twice its value and make blue and green half instead. You'll notice that I'm using 2.0 instead of 2. This is important because GLSL likes to use the same units in any math that it does. So let's go to our windowing trial, and now let's create a new shader that calls our red fragment. It'll return true because it was successfully created. And let's set the shader, and now our image is red. Let's do something a little more useful. In my actual CT viewer, there is a color spectrum called hot metal. I don't know if this is used for MRIs or anything, but I thought it looked cool, so we're going to try and duplicate that. So the first thing we'll do to try and duplicate it is just try and find a formula for going from grayscale to hot metal. I didn't find the formula I was looking for, so we can just try to mimic it ourselves. So take a screenshot of the color spectrum. I'm going to put it in GIMP. So I flip it upside down and I move it to the top, so that way as I move my mouse down the image, the pixel that I'm at will actually be where I'm at in the spectrum. So we make sure our spectrum is 256 units tall. Okay, so we can see it tops out at white. Let's take a sample halfway down. And we can see red is more than halfway done. It's at 180. So to find a normalized value of that, I'm just going to divide it by 255. And so let's make a point. So at half of my color spectrum, I have a value of 0.705, blah, blah, blah. Let's take another sample a quarter of the way down. We see our value is 90. I accidentally wrote the actual value instead of the red value. So let's make another point at 0.25. So right now it's not looking linear. Looks like it might have to make a curve to go from 0 to 1. So that'll make it a little bit harder. So take another sample, and we've already topped out at red 3/4 of the way down. So we can see at 150. So let's get the unit of this as well. So our x value is actually 0.588, blah, blah. And now let's get our red value, which was 210. So it is linear, it just looks like red reaches 1 before the value reaches 1. So we can see it's not as steep as 2x, steeper than 1x. So 1.4 seems to be the magic number. But because it's linear, we don't have to guess. We can just pull out our point slope formula from grade school and figure it out from there. And this will make it a lot easier for the green and blue because now we know we only have to get 2 data points to get the line. So let's do the same thing for green. Let's find 2 points. And then isolate the constants to find our offset. And we have the formula for green now. So lastly, let's do the same thing for blue. And we now have the formulas for all of our color components for this spectrum. So let's go back to our red shader. I'm going to rename it hot. And let's convert the functions for our colors into the language used for the shaders. So these are all going to take a floating point value and return one as well. And let's create a h function for heat, and we will take our grayscale value and map them to the correct red, green, and blue for our new color spectrum. And this image is a little brighter than the one in the DICOM viewer. And that's because I have it applied to my zeroed spectrum image instead of the full spectrum. So if we change to full spectrum, you'll see they are now the same colors. Let's now make this color spectrum work with our 16-bit image instead. And so the 16-bit image stores its high bits in the red pixel and its low bits in the green pixel. So you want to combine those into a single grayscale value and scale it down to mimic the levels of our other window shaders. Let's apply the shader, and it works. Let's now make it work with our full 8-bit shader. And so this only takes a value and then it offsets it. And now let's add windowing to our shader so it can window at a different level than what we rendered our original image at. And to do that, we take our grayscale value, we subtract the low end of the window from it, and we divide that by the window width. And so I'm going to do a lung window, which has a level of 0.3 and a width of 0.8. And so to get the low end of the window, I'm going to subtract half of my width, so 0.4 from 0.3, which gives us a negative 0.1. And my image does not look as bright as the DICOM. Hi, this is Daniel from the universe where everything goes right. Daniel realized that his images did not look the same when he applied his windowing, and this is because he was windowing with values from microdicom rather than values from AMIDE, which he's using to test against. Obviously, if I use the same values in both my online and offline DICOM viewers, everything looks right. Bye! Lastly, let's make our shader a little more dynamic so we don't have to write a brand new shader for every different window level we want. So that we're going to split up this long string and take certain key values out of it and plug them in at runtime. Now let's make a function called hot, and hot will take a type, it'll take the low end of a window, and it'll take the width of a window. So if our type is z for zeroed, we're going to concatenate all of our strings together, inserting the low and the width, and then only the red component of our color. If it's full, we do the same thing with the low and the width, but we want to offset our red component. And if it's 16, we'll call that high. We will want to combine the red and green components. And now if we try creating the shader with the values 0 and 1, it's going to complain because, as mentioned earlier, we don't have decimal points in our numbers. So it thinks we're trying to do math between a floating point number and an integer, and it doesn't care for that. So anytime you add numbers, make sure you always have a decimal point somewhere in it. And we're done.